Welcome back to the Explainer. Today, we're diving into an incredibly fun data structures and algorithms challenge, LeetCode 3756, concatenate non-zero digits and multiply by sum 2. We're going to take what looks like a completely impossible string concatenation problem and transform it into a beautifully optimized segment tree solution. If you already know your way around basic arrays and recursion but haven't quite mastered segment trees yet, well, you're in the absolute perfect place. Let's get into it.
So here's the setup. The problem asks us to take a string of digits, drop all the zeros, smash the rest together to form a single number, and then multiply that by the sum of its digits. Sounds pretty straightforward, right? But here is the hook. The string length, which we'll call m, and the number of queries, q, can both be up to 100,000. If we try a naive brute force approach, like actually scanning the substring for every single query, we're looking at m times q. That is up to 10 billion operations. Unless you have a supercomputer lying around, that's a guaranteed time limit exceeded. We desperately need a way to answer these queries in logarithmic time.
So actually pull that off, we need to break down the core operation. Let's just forget about strings entirely for a second. How do we mathematically concatenate two numbers? Let's say our left block is 12 and our right block is 34. To join them into 1, 2, 3, 4, we take that 12 and shift it to the left. We do that by multiplying it by 10 to the power of the number of digits in the right block. The right block has 2 digits, so that's 10 squared, or 100. So 12 times 100 is 1200. Add the right block, 34, and boom, you get 1, 2, 3, 4. The huge insight here is that concatenation, it's literally just math. And that brilliantly illustrates our very first big aha moment. This mathematical concatenation formula is inherently associative. What does that actually mean for us? It means the grouping of the operations totally doesn't matter. Whether you concatenate 1, 2, and 3 first to get 123, and then add 4 to get 1, 2, 3, 4, or you combine 3 and 4 first to get 34, and then concatenate 12 with that 34, the final result is exactly the same. Because it's associative, we can break massive ranges into smaller, bite-sized chunks and merge them back together in whatever grouped order we want. Since we're dealing with an associative merge over various ranges of a string, this is the absolute perfect signature for a segment tree. As a quick refresher, a segment tree is basically a binary tree structure where each node represents an interval, or a chunk, of an array. It allows us to pre-calculate data over these chunks, which slashes our query time completely down to a logarithmic scale. Instead of scanning a massive substring every single time, we just grab a few pre-computed nodes and merge them. But how exactly do we adapt this tree for our specific math?
Well, to make this work, our node design is absolutely crucial. We definitely do not want to store the actual astronomically huge concatenated number in our tree. We only need to track 3 minimal pieces of state to make our merge formula work. First, we have val, the concatenated number modulo 1,000,000,007. Second, CNT, the count of non-zero digits, which tells us exactly how many places to shift when we merge. And third, sum, the simple sum of the non-zero digits. And honestly, that's the whole shebang. Having this minimal state perfectly shapes our merge logic in the code. When we're combining a left child and a right child to make a parent node, the logic is super elegant. We simply add the lengths together. We add the digit sums together, modulo our constant. And for the main value, we apply that math trick we talked about. We take the left value, multiply it by 10 to the power of the right node's length, and then just add the right value. All of that modulo 1,000,007, of course.
Okay, listen closely, because here is our second huge aha moment. Unlike a simple range sum or finding a maximum, concatenation is not commutative. Think about it. 12 concatenated with 34 is 1234. But 34 concatenated with 12, that's 3412. Order strictly matters. When you're writing your query function, you have to be totally meticulous about merging subresults in strict left-to-right order as you traverse back up the tree. Let's actually do a step-by-step dry run so you can see this in action. Imagine our string is 10203004, and we query the range from index 1 to 3. That gives us the substring 020. In our segment tree, a 0-digit acts as this sort of invisible identity element. It contributes 0 value, 0 length, and 0 sum. So we merge the identity 0 with the digit 2, resulting in a value of 2, length of 1, and sum of 2. Merging that with a final 0 changes absolutely nothing. We're left with a final node value of 2, and an answer of 2 times the sum 2, which equals 4. Now what if we query the whole string from index 0 to 7? The segment tree recursively merges the left half 1020 and the right half 3004, shifting the left value by the right's non-zero count, and instantly giving us the total in O log m time instead of scanning all 8 digits.
Now, if you look at the structure for both the Python and C++ solutions, they're practically twins. You've got a build function to initialize the tree, a query function to fetch ranges, and that merge helper we just discussed. Having seen how the segment tree works in theory, let's step into the abyss of real-world debugging for a minute. We're going to explore 3 major pitfalls that developers naturally fall into before arriving at the fully optimized solution. Seeing wrong but plausible code is honestly way more instructive than just having the final answer handed to you. Pitfall number 1, the overflow disaster in your build function. A really natural first attempt in C++ is typing your concatenated number as an unsigned long without a modulo, and writing a while x is greater than 0 loop using x modulo 10 to peel off individual digits for the sum. But here's the catch. A long substring will silently wrap around. It completely corrupts. You simply cannot extract a true digit sum from a corrupted, overflowed number. Which naturally brings us to our third aha moment. And honestly, this is a massive concept in computer science. Never reconstruct from ruins. Once you store a value modulo a number, or once it silently overflows, those original digits are permanently gone. You can't peel them back off using division and modulo. You must compute that digit sum strictly from the original source string, entirely independent of the concatenated value. So developers realize this and fix the overflow by applying the modulo during the build phase. But that leads right into pitfall number 2. People often compute the concatenated value and then write a second, completely separate scan of the substring characters just to get the digit sum. This works numerically, sure, but scanning the exact same substring twice is just inefficient. The real fix here is to refactor your code to combine these operations into a single, clean for-loop pass over the characters, extracting both the value and the sum simultaneously. But wait, even with a single pass, we hit pitfall number 3. Time limit exceeded. Why? Because if your code does a full substring scan per query, you're running at O of range length per query. With 100,000 queries, numerically correct code can still be painfully slow. Numerically correct and fast enough are 2 entirely different bugs. Fixing this massive efficiency gap is exactly why swapping that manual loop for our segment tree, which gives us an O of log m time per query, is absolutely mandatory here. Let's look at the final damage complexity-wise. Because we pre-compute our powers of 10 and build the segment tree up front in O of m time, answering the queries becomes incredibly fast. Each query takes just O log m. So for Q queries, that's O of Q log m. Our overall time complexity is beautifully reduced to O of m plus Q times log m, and our space complexity scales super efficiently and linearly at O of m. This setup will effortlessly breeze right through the strictest time limits. Okay, let's wrap this up with 7 crucial takeaways from today's explainer. First, always look out for associative patterns. If you can group operations freely, definitely think segment trees. Second, respect the operation order. Concatenation is strictly not commutative. Third, minimize your node state to just what you need for the math. Fourth, trust modular arithmetic for multiplication. Fifth, remember to treat zeros as invisible identity elements. Sixth, never rebuild digits from reduced or overflowed values. And finally, remember that just because your logic is correct totally doesn't mean it's fast enough. Thank you so much for joining me on this debugging journey. I really hope dissecting these pitfalls helps you out in your own coding adventures. If you found this helpful, please like and subscribe for more deep dives into data structures. And I'll leave you with this final thought. What hidden associative properties will you uncover in your next DSA problem? Keep coding, and I'll see you next time.